Good afternoon, Wednesday 10, May 2023. What I've got here today is Vector Bundles of Mathematical Physics, Volumes 1 and 2 from Robert Hermann. And they're published in about 1970. And what they represent is, the title is Vector Bundles in Mathematical Physics. And the milieu is the differential geometry, and the jet bundles, the topological construct, the sheaves and the bundles. And so it kind of represents quite a development in the physics about the Yukawa potentials and about these great things to do with duals and the derivative about Jacobi, Hamilton-Jacobi, the vector fields and what they mean with regards to space-time. For example, as he mentions finite dimensional spaces with singularities, about infinite dimensional manifolds. And they're really pretty great. And they represent quite a lot of content that the idea is to reduce that then. So when we think about space-time, you got a continuous manifold, and why is that? Well, it's Euclidean space, and what is that? Well, you can apply it anywhere Cartesian space. You can make it a vector space, and this way we have a lot of available tools with regards to the theorems about vector spaces, and the orthonormal, and the linear, and the circular, and geometry, and all that stuff that happens to live in the Euclidean space also happens to all live in that. So then the vector field is the idea is that you say, okay, at any point on this flat space, flat in the sense that the metric is the same everywhere and it's defined and it's the usual measure and it's the real metric and Euclidean metric, then you can apply to that any kind of vector value at each point in the space. And so these are called the field occupation numbers, and or Einstein's material points. What are the points? In geometry's field, and the term field itself, of course, is overloaded. Field is a study. Academics is a field. Philosophy is a field. There's philosophies of mathematics and logic, and there's philosophies of probability and physics. We call it the natural science, physics. And then there's fields and all sorts of fields. And there's theories and their fields in their applications. So then we have theories and numbers and spaces and geometries and points and vectors and lines and types and categories and sets and parts and functions and operators and all these things that are first class in their fields and they're objects, and so they have models. And so what does all this theory result to for the structuralist? Well, the constructivist has what is called model theory. So model theory basically says that as soon as you have something that you can basically apply as representing each and every possible relation about something else, then it's a model of it. And that it is complete or incomplete or faithful or inconsistent, essentially, is whether it applies to all the things. The thing that models one thing, the thing that models the other thing. And so this geometry and space-time basically models space and with as well a coordinate of time. And that otherwise everything would just be universally parameterized by time. And so one thing that Hermann makes clear is that these are sort of like the Lagrangians, systems, dynamical systems parameterized by time. And so getting into this a little bit, then when we have our vector field, then you can think of a couple different ways that the vector fields have their values in the space. For example, they might just have 0. They might be a vector space itself. So in a sense, you can attach a vector space to this vector space, and it makes a higher dimensional vector space. When is it that the continuous manifold is just an extension of the continuous manifold? When, for example, the 0 vector, which is the identity and the additive in the vectors, have it like so. And in the vector space, then we also often have a basis, which is basically the basis for the multiplicative identity. So you got the additive identity, better known as 0, the 0 vector. And then whether this vector field on the manifold this space, that you would take a particular space and say this is a continuous manifold and it's Euclidean or dot dot dot. And then on it you attach this higher level vector space, and it's just it can be continuous, it can be discontinuous, it can be scalar valued, it can be vector valued, it can be tensor valued, it can be matrix valued, you can have any field occupation numbers that represent all the quantities and their relations and their interactions together that there is. And so then the idea is that there's either the zero vector is the vector, or other times you might just have a vector field where it's one everywhere, that it's there's basically it's populated first with vectors that are normal to the space everywhere, and they have value 1.0, and then they can, for example, rotate about that. Or that otherwise, that then when you have any curvature in these field numbers is so defined as the way that higher order surface sits on the regular surface. And so you can make that anything to do with any kind of quantity that's quantifiable, that you get a quantity by quantitizing something. That's kind of a made-up word, but it reflects the fact that otherwise, after about the qualia, there needs to be some means to give an analytical character, which is a quantity. And then in all these formulas and their equations, when they have the combined terms, whether they're composed functions, whether they're expressions, whether they're the results of derivations after identities in the additive and identities in the multiplicative and annihilators in the multiplicative, triangle rule, quadrature, linearizations, mensurations, integrals, derivatives, the raw differential and the derivative, all these different things are quantities in their expressions. And then the idea is that whether they can be considered apart or whether they can only be considered as part of a notation and a convention makes for how these formulas are connected together. It makes them whether they're composable and whether they're separable, and whether they're integral and whether they're degenerate. And so these are the kinds of things that get into defining what is the content of these vector fields. So there's mathematics' field is a complete ordered field. Usually it's the real numbers as defined by addition and multiplication, these groups, their inverses, subtraction and division, though not closed by zero, as everybody knows, that these are the usual way that we have what's called the field of algebra in mathematics. And then the usual vector field is a real field in physics, and it's 3 dimensions for space plus 1 for time, or just array of time, backwards say. So that everything going forward is just not yet arrived, but then as time goes on in infinitesimal steps, it occurs everywhere, right? That these are the kinds of things that then attaching this vector field up on top of this manifold is basically to say you can start with any kind of space and then attach a vector field to it. In fact, you can just start with an empty space and attach a vector field to it. So in a sense, it's a vector field as a vector field as a vector field. And then for real valued variables, infinitely divisible, unbounded in extent, they're real numbers, it's a complete order field. And then a lot of what goes on then in the space of these things is about the continuous functions. What is a continuous function? You mean a function that I draw and it's smooth and I can put down the pencil and trace it and lift the pencil, and any one of those is a curve and also a function in geometry space, for example, a plane? Yes and no. Because all the continuous function cares is that a sufficiently small change in the domain and according to the order also of the domain that's totally ordered or well ordered or linearly ordered, that has trichotomy, that there's always less than, equals, or greater for any 2 different values. That then that gets into the continuous function is just that for any small enough change in the domain, it's just correspondingly as small and the same ordered change in the range. And so you can have a continuous function and you apply it to something like the rationals, which are not continuous. They have discontinuities everywhere in terms of not being a continuous domain. So that's for separating what the notion is of a continuous function from a continuous domain. Then in terms of these spaces of continuous functions, then there's the functions that are also differentiable everywhere. And so they have the derivative exists, like what is the slope of this function in its plane, or its partial derivatives, given that you attach an orthonormal vector basis at right angles in any particular one, that there exists its derivative in that direction according to that ratio in that quantity. And then there's these family functions that make, if they're infinitely differentiable, it means you can always arrive at the differentiable about that. And well, what is the division by zero in that world? Well, it's singularities. And a singularity is like an asymptote, like a vertical line. Its derivative would be infinity. So whether it's an Archimedean or non-Archimedean, or whether you need to have meromorphic analysis or free analysis on the plane to deal with the singularities and this kind of thing, or torsions, which is kind of like a Mobius strip. Something took a half turn or whatever, but then it's projected on the other side, or the spiral space-filling curve, or these kinds of things. This is this family of continuous functions, and so most of the theorems are defined as about these continuous functions and their derivatives and the existence thereof. And when things become negligibly small and you call them zero with respect to analytical character, so that various applications can result ordering a rank from higher level formulas, higher order ranks of polynomials, higher order in the terms, to lower ones so they can be solvable. So they can be sensible and then fungible and then tractable. So that's really quite standard, and coming out of real analysis, that's very much the usual course. And then when things happen and go to infinity and this kind of thing, or in the infinitary, it's quite a special thing, because then it reflects that what for that to still maintain the analytical character, that gets in all these things that we've been talking about, like the Jordan measure, the Dirichlet problem, or Dirichlet function. The Dirichlet problem is about finding harmonic functions on the Poincare sphere, but it ends up being that if there exist those besides the usual sums of harmonic functions, it's that there are particular non-standard functions, or functions in the unbounded, in the infinite, that actually are alternative solutions to the Dirichlet problem that exist. And so already physics in its fields has lots of formalisms and conventions that start to deal with infinitesimals, almost always between 0 and 1, and adding almost always exactly back up to 1, the extent and length of them, that their analytical character is just like the raw differential, and it's built up this way, and it's like so, compared to when otherwise, well, we either have differentials that are neglected or differentials that are not neglected. And whether those add up to really analytical character or not, or are non-measurable, or apeiron, the Greek word for unbounded and infinite, but back in that time also meaning non-finite, and thus not a number, not a thing. That these kinds of methods in the mathematical physics are very widespread, and these books by Hermann are traditionally standard kinds of contents of the courses that go into the higher order things. And so these fit really well with this differential analysis we've been talking about, and the symmetries and the sheaves and the submersions. Oh, here's this. This is a little bit different. And the pseudo differential. This makes some of these developments in the field, because when you take the infinitesimals in a line and you call them iota values, and so each integer is basically the next infinitesimal's value. 1 iota, 2 iota, 3 iota, after 0 iota. So from 0 to infinity in the integers, that's 0 to 1, these iota values, that the limit as n goes to infinity of n over d, as n goes to d and d goes to infinity, it has extent 0, 1, it has density, because in any neighborhood there's infinitely many neighbors, in any standard neighborhood, and in any contiguous neighborhood there's previous and next, except for 0 and 1, and the inverse of that function. So there's extent, density, and then completeness in the usual sense that according to being complete is that the least upper bound is the property so established, and it's so for these iota values, because the least upper bound of any given value is the next one. It's trivial, which is very nice. And then it ends up with being measure 1.0, and that's because its extent is 1.0 and its measure is 1.0. There's sigma algebras about a length assignment of these values that basically make for the sigma algebras to make formalized for measure theory, that this is also what can implement the Jordan measure. So the Jordan measure today is kind of poorly understood, because without this kind of formalism making up this countable continuous domain, and the complete order field as a continuous domain is an uncountable continuous domain, because this particular function is unique, it has uniqueness results, it is not Cartesian, so it can't be reordered or otherwise taken apart, or it's only this particular line drawing in effect. That there's continuous domains of the line drawing, continuous domains of the field continuity, and in the continuous domain of the signal, which is essentially that when you have the rationals, then twice that is continuous domain, because it's kind of like an extension of the Nyquist theorem, that it implements a description of a wave at that frequency, that double that wave is sufficient to reconstruct it, and so then we call that signal continuity. So in this sense, then, there's already at least 3 definitions of continuity in play that go into the foundations of mathematics. And then for physics, then what we call that is the line continuity is called Jordan measure, the field's standard analysis is called standard real analysis, and the Dirichlet function, which is 1 at rationals and 0 at rationals, gets involved with the signal continuity. Then about these invariances that have to do with the continuity laws, which make conservation laws, that symmetries invoke basically crossing across boundaries thanks to the perpendicular and orthonormal continuity laws for conservation laws about symmetries. These end up being that what results is the way to assign these continuous domains, their realms, to each of these regular constructions and conventions in physics. So then when we get to something like the non-standard functions, like the Dirac's delta function, it's well known that you can build it as a limit of standard functions. Whatever has in its area 1, just like any distribution that's centered at 0, and then there's a parameter that basically shifts it to the left or right. It's u, or as part of our differential analysis and the usual methods, and the existence and of solutions, and the proviso of solutions, and the crunching out values with sensible, fungible, and tractable solutions in the differential equations, that what results is that it's a non-standard function. Because in the limit, or the continuum limit, that function is like a flat line with a spike at 0, the spike goes to infinity. Well, la-di-da. But the kicker, or the surprise, the beautiful part, is that as area equals 1. So the Dirac delta has underneath it, it's like a square that's shrunk as it grows, splitting into half, stacking the halves on top of each other, till it goes to 0 width. It still has area 1. And so this is an example of a non-standard function. Now this line drawing, or equivalency function, or sweep, has this similar type of function. It's a non-standard, it's not a real function, because the complete order fields elements that it also maps to, it has an extensibility about it in the range of real value variables, is that it only attaches to 0 and 1, and then everything else just kind of exists by an existence result, and it has trichotomy and this extent, density, completeness, and trichotomy and measure, that these things make it a continuous domain. That then there's that the funny thing about this function, though, is that it would look kind of like a triangle of from 0 to 1 in the real value, and you're splitting that in half infinitely many times until there was, and just extending that out in the integers. The limit of n over d is n goes to d, as d goes to infinity. That's a simple definition. And you'd think that its area is 1/2. But when it's all the way divided, not just as it's dividing, but when it's all the way divided, its area equals 1. So it's another one of these non-standard functions of central and primary importance, this equivalency function. And then there's some other properties that make it so that it's a PDF and a CDF from probability theory of what distribution? Of the integers, of the natural integers at uniform random. Well, that can exist. Isn't that infinitary? Yes, it is. It's extra standard infinitary. Oh, well, that's an interesting property. What about what about that in higher dimensions? Well, it makes a spiral space-filling curve. In infinite dimensions, it's just like a dot at the origin, and it fills in outward, always out in the dimensions first, and then as it fills in, it's infinitary that way, and infinitary outwards till it fills in the unit ball, pretty much. Well, what is this a singularity? Yeah, as a matter of fact, just like an asymptote, it's also a singularity. Well, that's kind of remarkable, isn't it? For a mathematical function of central importance to all matters of continuum mechanics analysis, yeah, it's a thing. Oh, well, what other properties does this spiral space-filling curve have? Well, one interesting about this with this line drawing is that it's its own antiderivative. E to the x I'm familiar with. You mean like if I take the derivative of e to the x or the integral of e to the x, I get e to the x, or e to the 1x, carrying it down, carrying the power of the variable down. Or if I integrate it, I get e to the x plus c, carrying the value of the variable back up and putting up in the power, the coefficient on the variable. It's its own antiderivative and its own integral too. And it's infinitely differentiable. So this function is also, it's very surprising. It has these other properties that establish what are otherwise uniqueness results in these various fields that are just now they're distinctness results. And so as basically the very basis of standard non-standard analysis, this continuum infinitesimal analysis is what boils down to make it so a way to have a pretty solid intuition. And then in terms of all the standard analysis and these kind of texts about real analysis and dynamical modeling, mathematical physics and its vector bundles here, as Hermann is going to tell us some more about, it provides a way to attach to the conventions and the notations of those things, these things. And so that when you have this kind of idea, it's like, well, it's an alternative to uniqueness for functions that are their own antiderivative. And it's an alternative to uniqueness and existence itself of functions that are uniform distributions of infinitely many naturals. And it's a discrete distribution, and it's a continuous distribution. It is a PDF, and it is a CDF. The cumulative density function or probability distribution function. It is a singularity. Its curvature is the exact curvature that science looks for when it says it's 1 over r. It gets into what is the real gauge, what is our gauge. It matches up with Descartes' theory of vortices and looks just like one. It's almost like it was read off from that, but instead it's postmodern, paleo-classical, retro-classical, but built in the theory after axiomatic set theory and descriptive set theory that adds up after that as a non-Cartesian function. It's great. So that's line continuity, and then there's field continuity, should be familiar to everybody as the usual algebras course and the usual real analysis standard course. The equivalence classes of sequences that are Cauchy are real numbers, and they make a continuous domain. And then all our functions are as continuous functions with respect to any continuous domain. All the theorems of continuous functions pretty much apply to continuous domains. And then the signal continuity is another kind of thing, and it really reflects then, going back to these continuity laws and the conservation laws and the symmetry laws, what makes sense for these being now continuity laws instead of conservation laws and symmetry laws and matters of reflection in the discrete and finite, that it still results analytical character that's well defined. That's great. So reading Hermann, when I started, I got this volume 2 the other day, and then I picked up this volume 1 today. And this one's a hardback, the other one's a softback. They usually have library bindings. And in this case, it was published in 1970 in volume 2 here. Let's see what that says. It's in a series. It's from Mathematical Lecture Notes of W.A. Benjamin. And this was also published in 1970, or that's his copyright. And on page 110, he had a pretty interesting thing. Let me read from the preface. Here's from the preface from the author. Preface. As in my earlier book, Lie Groups for Physicists, and here we've been reading this, this is all about Lie groups here as it starts. I mean these notes to introduce to physicists, other scientists, and perhaps even to mathematicians certain ideas arising out of contemporary Lie group theory and differential geometry that may be helpful to help them in their own work and may contribute towards the description of the physical world in mathematical terms. The idea of a vector bundle, usually also associated with the differential manifold idea. Here, this is the vector field, and these bundles on the vector field. From topology, we have these sheaves and bundles, which have various contour theorems about them and things from topology, is one of the keystones of contemporary mathematics, appearing in the theory of PDEs, see Palais, algebraic topology, see Atiyah and Husserl, and algebraic and differential geometry. It expresses some of the most basic intuitive geometric ideas in precise and conceptually clear terms, and the mathematical formalism developed over the years for the study of vector bundle related concepts often leads most directly and simply to the clarification and solution of those problems that can be phrased in vector bundle language. As was pointed out already in Lie groups for physicists, the vector bundle idea is also very natural in physics, appearing at least implicitly throughout both the classical and quantum theory fields. Anywhere that there's continuity because it's geometrical. For example, indeed, the very notion of a field itself, as much as it can be formalized, clearly involves vector bundle ideas. Since one thinks of a field in primitive terms as a function assigning to each point of our space several numbers, the field parameter is at that point. So here what he calls field parameters, you might call field occupation numbers, you might call material points, you might call values, you might call 0 or 1 as a basis for a field that when it's relaxed or under torsion would carry out in those terms about 0 and 1 being different, about attaching an infinite value to each of these terms, or like when light speed is the maximum for special relativity, here we're going to put the difference between it and c, and whether that's a natural unit, and dot dot dot. The field in this field parameters at that point. In terms of our jargon, this would translate into a definition of a field as a cross-section of a vector bundle. So here is defining the sections and sectioning, because the idea of the vector bundles and taking sections of them is then that you can assign them properties that make for reassembling them and their analytical character to implement for them the intermediate value theorem, so you can have the fundamental theorem of calculus, so you can have the fundamental theorem of the integral and integrate them or differentiate them. And whereas in operator theory becomes very powerful when it gets above such notions as these closures, that it can then make closed forms for lots of application of what's called operator theory. It's pretty abstract. Model theory, operator theory. Field as a cross-section of a vector bundle whose base is our space and whose fibers are vectors describing the possible values of fields at points of space. As in Lie groups for physicists, I hope that the presentation is more informal than is customary in mathematics books, and that is interspersed with physical applications and ideas will help the reader penetrate more easily into the interesting concepts provided by contemporary mathematics. In this approach, proofs are not important for their own sake, but only as guideposts in a new territory. So, kind of like Mogan's reading from the nonlinear electromechanical effects and applications, what you can expect from Hermann is that he makes developments and their derivations, and they're not always immediately spelled out because it's expected you know all the conventions that make for valid verifications of these derivations or proofs going along. In general, I think it is useful to keep in mind Poincare's division of mathematicians into two categories: the geometers and analysts. Now, this does not mean people who study geometry and analysis, but refers instead to a division between those who prefer one type of reasoning to another, say those who like broad, qualitative, intuitive, i.e. geometry-like arguments, and those who treasure precise, completely logical, deductive sorts of mathematics. They're the same. Presumably, this arose in Poincare's mind to explain his disagreements in matters of taste between his contemporaries like Cantor and Weierstrass. Although he spelled Weierstrass without the usual second E, I'm not sure if that was typical, who were engaged in the process of driving out from the foundations of mathematics all the sloppiness that Poincare found so stimulating. So see here, I've driven out, as Hermann puts it, from the foundations of mathematics of some of this sloppiness about the continuous domains. Line continuity, field continuity is standard, and then Cantor space has this complement, this alternative view called square Cantor space, and it's a non-Cartesian function about it's about a non-Cartesian function about the diagonal and the anti-diagonal. And then there's Weierstrass, who Cauchy-Weierstrass really formalized a lot of great important things. So our usual notion that the intermediate value theorem follows from Cauchy-Weierstrass is so standard. But Hermann, it's nice to see a physicist explain what's going on about the foundations of mathematics, and that usually physicists are mostly just put out by these perceived absences of real analytical character according to these definitions of continuity in mathematics from physics. Mathematics owes physics this kind of apologetics and paleoclassical retrofit modernization. Today, the analysts hold power. Most mathematicians recognize and practice only work that produces hard-headed, precise theorems that are deep and technically difficult, and that contribute to the solution of a problem that is recognized by a consensus of mathematicians as important and difficult. If it is a famous old problem, so much the better. It is in the nature of things that a geometer will not do this, at least as his main activity. It seems to me, however, that if mathematics is ever to interact again with the outside world, say with theoretical physics, at least, we must revive the geometry spirit, working in, of course, the advances in technique and formalism that have been provided by the labors of the analysts. This book is written in that spirit. When writing Lie groups for physicists, so this is vector bundles in mathematical physics, but there's also Hermann's Lie groups for physicists, I could assume that the physicist reader already had some familiarity with groups and representation, since some of this material is taught in quantum mechanics, elementary particle, and solid-state courses, and there existed several excellent review articles by physicists which bridge the gap between my point of view and that held by most physicists. In this book, I must confess to a feeling of less confidence in my position, since it will be necessary to use at some point in the development the formalism of differentiable manifold theory. Now, I am confident that in the long run, this will be taught to every student interested in physical applications, and even at the undergraduate advanced calculus level. This trend is exemplified by, and no doubt will be stimulated by, the recent books by Spivak and Loomis and Sternberg. At the moment, all I can suggest is the reader who is completely ignorant of differentiable manifold theory read, at least poetically, the introductory material that does exist. Loomis and Sternberg, Auslander and Mackenzie, Flanders. Possibly consult the review articles written by physicists involving differentiable manifolds, mostly in the literature of general relativity theory of the last 5 years. See, for example, C. Troutman. And consult the introductory parts of my book on differential geometry. If he perseveres, the reader will ultimately find that formalism provides a marvelously unified set of tools for the description of those natural phenomena that involve a combination of geometry and the differential integral calculus. Finally, the reader might find some of the material in my monographs and series of articles useful to supplement what is provided in this book. I'm indebted to M. Cack and H.P. McKeon for their hospitality at Rockefeller University while this book was written. I would also like to thank Mrs. Altazap for her excellent typing. Robert Hermann, New York, 1970. Now, one term you'll often find in Hermann is differential integral calculus, and so you might also hear of differo-integral systems, and it basically reflects his operative theory in raising lower the rank of these things about the inner and outer products, where it results that either derivations are the inner products and integrals are the outer products, or vice versa. And so the TOC table of contents has general concepts, spaces and mappings, ... algebras and modules, ... differential operators on vector bundles, jet bundles associated with modules. Then chapter 2 gets up into the jet bundles associated with fiber spaces and the Lagrangian. So the Lagrangian gets a better definition about page 110. And that's kind of where I started reading here, is up in chapter 3, which is called, there's section 6, the principle of minimal interactions. And then chapter 4 is Euler-Lagrange operator. So that's where he defines it. Chapter 5 gets into the symplectic structure. So the symplectic has to do with these symmetries, and the plexus of these things, you know, the locus, the focus, the plexus, and the symplectic is good. There's got quite a lot going on. So you can find that in the geometric algebras. Pizzaglia and all the great works that have come out expressing a lot of these things instead of like the complex analysis, but the hyper-complex after Elie Cartan's great works in reflections and rotations, the symplectic, about the things here. And then by this point, he's getting into the Heisenberg picture and canonical quantum field theory. So here, where we've been reading that is from the reading from the path integral. And so a lot of the talks already that have been here have been about this differential and rounding up differential methods in terms of sheaves, submersions, and symmetries, and this kind of thing. And then there's also to be figured out how there's analogs of the differential in the integer valued functions, like the differences of squares, the differences of cubes, the harmonic and hexagonal numbers, the Cuban primes, those ways to look at all these things in the integer functions that are usual roots and powers that have great things about them. And then going on in this book, then we get into the Poincare invariant. And so at some point in time, he'll have introduced some geometrical intuition and instinct about Poincare. And so there's lots to be learned from Poincare. And it gets up to Fock space and Fock-Ivanenko, and then we'll be talking about, and then it ends with Clifford algebras and fermions, which is where some like the Majorana fermion was like, Ettore Majorana invented a mathematical model of just a simple complex thing, and thus he was able to predict the existence of a particle, and lo, it was found. It's its own antiparticle. It's a weird virtual particle, but it existed according to being discovered in his data. Then he disappeared. That's into various things. It reminds me of Perdi Lonesto. He was a pretty great mathematician in the Clifford algebras, and a physicist. And one of his favorite things to do was find people who'd written physical papers that were garbage and point out why they were wrong. I don't really find that my favorite thing to do, but I really enjoyed that guy. Page 110. The principle of minimal interactions. So the principle of least action is the usual idea of physics, that nothing's free in the sense that everything is free to go about just as it does, not to arbitrarily implement the perpetual motion machine where energy or work makes it a closed system has violating the conservation or continuity laws. That's boundaries. Principle of least action is about it's one of the most fundamental principles in physics. Principles of conservation, principles of least action. And so this minimal interactions is going to be described here by Hermann. Section 6. Now we will discuss the way that linear connections are used to introduce interactions between Yang-Mills type fields and more traditional linear fields. This is the principle of minimal interaction. So these Yang-Mills fields are going to have various notions of their connections and the way they have actions and the way they influence higher order terms and the nonlinear terms and the what would otherwise be vanishing terms, but because of interactions in fields exist and have non-zero, non-negligible analytical character, these are things with respect to traditional linear fields, which are closed and solved, and often, in the absence of otherwise these interactions, in first order approximations, very accurate. But always, whenever there are approximations, always with a non-zero error term. So parenthetically it says, this is the principle of minimal interaction. Let pi e to the m be a vector bundle. We have already defined j to the l e, the bundle of first order jets, and shown how elegant it is to describe a Lagrangian system parameterized by time, including when it's implicitly parameterized by time, as a real valued function on j to the l e. Consider two linear connections, grad prime, and C sub tilde E, and a Lagrangian L in F of J to the L E. The principle of minimal interaction assigns to the pair grad prime and to the Lagrangian L a new Lagrangian L sub grad prime. The Euler-Lagrange differential operator associated with this Lagrangian physically represents the results of interacting the field generated by the Euler-Lagrange operator associated with L, and the field represented by tau equals grad minus grad prime. So this is where in the PDEs and what you want to compute the gradient and this and that, and the whole idea of the Laplacian is making for linear solutions that, and it's very closely tied to the metric, and this to triangle rule, Cauchy-Schwarz inequality, and how that is used for all such manners of these conventions and the connections of things and the continuity and establishing the cases for the immeasurability of quadrature and all this kind of stuff. So here he's saying that there's grad and grad prime, and so the gradient here has these nonlinear terms, grad prime, and their difference is this, represented by tau equals this difference. To see how L sub grad prime is constructed, we must examine the structure of J to the L E in more detail. To this end, suppose that a single linear connection, grad in J to sub L E, is given. Recall that a psi in gamma E vanishes to the first order. So here's where these terms kind of are negligible or vanish or are small at P if A psi P equals 0. B, all first derivatives of psi vanish at P equals 0. And so this gets into this harmonic function theory, and the idea is, well, really in the Poincare sphere, is it really unique that harmonic functions add up to the Poincare sphere, an outline? This is establishing that is so in this linear case. So in terms of this linear is part of the bundle, it's so. It's Laplacian. Now, condition B can alternately be expressed as follows. B prime. Grad sub x psi sub p equals 0 for all x in Vm. Then, given x in Vm, we can define a mapping. Grad sub x little p is a mapping j to L to E, that vector field's jet bundle. P goes to E to the P, for P a point. By assigning to little j sub L psi P to the L the element grad sub x psi P of E to the P. All right, so that's kind of when you see these mappings. Sometimes like we're gonna make an assignment so that this x to the x tilde is they're no different, and that so that later we want to take that down because we don't want to be considering how they got assigned that way, but just stand it up back that is the thing. So this is otherwise maybe better represented in some of these continuity conventions in the standard non-standard, make it extra standard, super standard. And that's the way we can look at some of these things. Here in his alternate definition, he's just made it so that he's got an intuitive handle to it from some of his other methods. And then he says, then he gets in some definitions, and theorems, and a proof about the Christoffel symbols. So these might start to become familiar in their methods and analysis from Mogan about bundles and projections, arbitrary vectors, coordinate systems, and now we can explain and so much involved. Basically, the result that formula 6.8 says j to the L of E sub P equals j sub H to the L of E P direct sum j grad to the L E to the P. So, and this is what he says was it should be clear from formula that a psi of the form other formula can be chosen so that the formula is satisfied while psi sub p is an arbitrary vector on EP. This together with 6.7 then proves that this direct product, the direct sum, where it's kind of like there's inner and outer products, and then this direct sum makes for a convention is about whether it's inner and outer and brought back down, or that the direct sum is to be defined. It's basically the plus with a circle around it is the direct sum, and times with its circle around is the direct product. The rest of the statements on 6.1 follow readily from 6.8. Now we can explain the principle of minimal interaction. This identity in direct sums implies that a connection grad determines an isomorphism between j to the LE and the direct sum bundle j sub h to the LE plus E. And so it might be kind of thinking of that's like, well, the one side is for the continuous manifold and the other side is for the vector field on it. Okay. If two connections grad comma grad prime are given, one derives two such isomorphisms, and an isomorphism alpha prime grad comma grad prime of j to the LE with itself. So that's about kind of these notions of the assignment, I think, and the extensionality, what so results after these different conventions that they add up to having the same convention, and then it becomes tractable to this operator calculus, and it's possible to get it. So then how we continue, it says this isomorphism, and an isomorphism is basically anything that preserves a structure, same iso shape morphism. Same transformations, same transformation. So isomorphism is usually very overloaded, and it's used to express any kind of mapping that kind of preserves character. It does. And then in group theory and algebra, of course, it gets in particular groups, then there's only particular admitted things that are isomorphisms, homomorphisms, same, diffeomorphisms, different, these kinds of things. This isomorphism will be constructible in terms of the difference tensor field, tau equals grad minus grad prime. So again, he has this difference tensor field as all the nonlinear contributions, and that are any different than the linear contributions. So you might sometimes think of, in terms of constructive and destructive, that the nonlinear contributions really are the linear contributions. That's the idea of the theory of sum potentials, or theory of sigma potentials, theory of omega potentials, that first of all, that there's some potentials that add up back down to the linear. But here he's explaining and making it clear that this difference exists. And then you basically have that the zeroth order, or what was the linear part, the difference of that part no longer exists. So then you can reduce and rank and form all the stuff that was otherwise the first order thing, and drop that down, and then everything kind of slides to the left with what's left in terms of 0 or 1 on that first term, and reducing the rank of the resulting system to define it in terms of these things. Before making this more explicit, perhaps it is relevant to discuss in general how such isomorphisms are constructed. Section 7, isomorphisms of jet vector bundles and the principle of minimal interaction. As we have just seen, the principle of minimal interaction leads to a linear bundle isomorphism, alpha equals j to the LE plus j to the upside down TE, or perpendicular, that usually indicates, which is the identity map on the subspace, and it's the mapping of thereof. So it's a dual. It's the mapping of it to its dual, which is the identity map on the subspace j sub h l e to the p, or j to the LE. If L j to the LE goes to R is a Lagrangian, one can construct a new Lagrangian, alpha star L, by the rule, alpha star Lj equals L alpha j, for j and j to the LE. So this is a composition of these functions. He's making a new Lagrangian. It's still parameterized, but at the same time, and it's making this mapping. He says, we will now make this more explicit in terms of a local product structure for the bundle. And when we say local, that's kind of arbitrary, because all this stuff that's local and non-local gets in the whole dichotomy of the point and local and global and total. And a coordination of the base manifold M. This coordination is whatever establishes the metric and the angles, the orthonormal Cartesian coordinates usually, or whatever is working in the coordinate system that makes for two ordinates, two axes, two ordinal valued things, number valued things, their relations under rotations. and reflections, and a coordination of the base manifold M. Our aim is, of course, to calculate the Euler-Lagrange operators associated with L and L sub alpha. To keep contact with the case of interest in quantum field theory, suppose M is R4 with coordinates x equals x mu. 0 is less than mu, v is less than or equal to 3. Let psi alpha, this series, sequence psi alpha, 1 less than a, b less than or equal to n, be an fm module basis of gamma e. So this is this coordinatization, this is this orthonormal vector basis, and the module is establishing what is maintaining those. I would have to know better what is a module because I've skipped it. But it's whatever as a model makes this module, you know. And with our simplest usual classical linear things, it falls down to much usual, more easily understood things like coordinates and geometries. This is just in the higher order up above these vector bundles on these continuous manifolds, these spaces on them. Now we and he says set delta sub mu equals d to the, it's d sub mu equals d to the dx mu. So this is assigning just the variable notation, and so d in dx mu is like the partial differential operator that so many people would then read off as the inverse of dx mu. Now we recall that j to the LE is a quotient of gamma E cross M by a certain equivalence relation. So here's making use of the fact that it's very well understood for the cross product that it's pretty direct. Thus, any real valued function on gamma E cross M that is constant on these equivalence classes make it so that it can be erased in terms of the value underneath it, that any member of the equivalence class is equal to any other member of the equivalence class, and a member is only in one equivalence class, and so differences can be determined according to whatever is according to the value space of this equivalence class. So here we can see Hermann very carefully and delicately talking out how it goes that there are things to do with the extensionality and intentionality of the models, physics, the mathematics, the foundations, descriptive set theory, axiomatic set theory, these continuous domains. Equivalence classes will pass to the quotient to define a function on j to the LE. As examples of this construction, define functions, series phi sub a mu, as if psi equals f sub a phi psi sub a, with f sub a in fm, this module, then a phi sub a of psi comma p equals f sub a p, and b phi sub a mu of psi comma p equals d mu, or d to the dx mu, f a p. So he's kind of set up the same thing that you have when regards to the definitions that were before this principle of least action, or principle of minimal interaction. Now these real valued functions, i.e. psi a comma psi a mu on gamma e cross m, pass to the quotient to define functions on j to the LE. We'll not use any special notation for this, but hope that the reader can keep things straight. In a usual formal discourse, then it would be a matters for annotation and to establish what sections maintain these same conventions and keep things straight, as he puts it. Suppose now that L mapping j to the LE goes to R is a Lagrangian, and that d sub L of gamma E to the gamma E is a corresponding Euler-Lagrange differential operator. So yeah, this involves all the previous things, or mapping adapters to them that make it possible to have these in place for what they contain as being modeled by their geometric form let out. Otherwise, what so results is necessary to be figured out for these higher level constructs. If psi is a member of gamma E and phi sub ax equals phi sub a, quantity j to the little j to the L psi of x then of course, phi of A of D, this differential operator of psi x equals d of dx mu, or this d mu, L, the Lagrangian sub A mu, of this quantity phi comma x comma d phi x. So it's the Lagrangian is a differential system, and so it's defined in terms of time, and it's a function in time, and it's implicit as about that, and otherwise that it results that anything that ends up being is a function of time itself in terms of the propagator and this action, and minimal interaction ends up being a linearization of sorts, or otherwise those terms, so that this minimal interaction is going to provide two linear views to help assemble a bunch of the nonlinear part with the linear. And the approximation minus that quantity minus L sub A of phi x comma d phi x. So this is reduced the order of the term, so it's got in front of it like the differential of it, and then it's minus in this difference term. So that's interesting how it makes it so, and it could be kind of reversed if you kind of made the difference the other way. So it could reverse this equation in a sense, and then whether that's to be meant to be just to make it simple, that in terms of when the partials have to come back together, there would be like or time like, that in the usual metric, in the Lorentzian, then we have that we subtract the t term in terms of the x terms, this time term, the space terms, or vice versa, that we would have to just redo the whole derivation backwards, but maybe then it would be more clear why it adds up instead of down, or vice versa. But anyways, our goal now is to compute the operator, the Euler-Lagrange differential operator, d sub a star L, where the a star was read off earlier, where a star L is given by 7.1 that we read. Now, j sub h L to the e is determined by the following conditions. J sub h L e, the set of j in j sub L e, such that phi sub a j equals 0. And so this makes for these continuity and conservation conditions, because anything that's set to 0 establishes a continuity law either way, because anything from the left has to go through 0 to get to negative numbers, or vice versa, and anything from the positive has to go through 0 to get negative, and anything from the negative has to go through 0 to get positive. And that when you have numbers between 0 and 1 and multiply them and take their powers, that goes to 0. And so when there's built up this analytical apparatus on one side that will keep it in those bounds, and on the other side will be in those bounds, and then they both tend to 0, they meet in the middle. So then that's what ends up being this usual result of how this isomorphism is built up, because in the one shape of this, it's like so, and the other shape is like so, and then they're both bound down until they end up being on either side of this difference, meeting in the middle of 0. It's a continuity condition. Suppose that alpha star of phi A equals alpha sub AB phi B plus alpha AB mu phi B mu, and alpha star phi A mu equals alpha A mu B phi B plus alpha A mu B B phi B B. Alpha star denotes the dual map. This f of j to the L e goes to f of j to the L e on functions induced by the map alpha. Now the condition that alpha maps fibers linearly, so we get into linear independence, and that being a key thing, and that it makes everything else so possibly soluble linearly, is equivalent to the statement that the coefficients of alpha sub AB, alpha sub AB mu, alpha sub A mu B, alpha sub A mu BB in 7.5 are functions of x alone. And this is about the interaction terms, or when there's implicits, when a function is parameterized by the inside the function is parameterized by its value. The point is differential again. It's differintegral. It's differential integral, as Hermann puts it. It's implicits, or it's reformulating itself. reformulated, are functions of x alone. Here is that they're not. It's linear. There's no otherwise dependency or variability in these things. Let us look for the additional conditions that alpha leave fixed to the elements of J sub H L to the E, L E. This condition obviously is that 7.5 takes the following special form: alpha star phi A equals alpha A sub AB phi sub B, and alpha star phi A mu equals alpha A sub A mu B phi sub B plus phi sub A mu. So here what is defined is that, according to these, then it works out that then you can algebraically cancel these other things and back and forth, and all the systems it makes for algebra means to get to a reduced form. Given that these hold, these become then later throughout ever after this particular derivation what must hold. Now, as for any function on the manifold J to the LE, we have dl, the differential, not the partial differential, equals L sub A d phi sub A plus L a sub A mu plus d phi sub A mu. And so this is after the operators. It's like, well, I'm using these conventions, and the raw differential is up in the operators because it's a convention in the differential and the integrals. So I can then use this additive formula and make it so and hold it up and feel like it's going to stay so because all these other things are going to keep it clear, where otherwise that would just be kind of like making a house of cards and expecting to be able to change one at all and have it tip, because the house of cards is fundamentally an astable structure, and any change to it will make it fall down. With L sub alpha equals alpha star L, we have dA star L equals alpha star L sub A and d alpha star phi sub A plus alpha star L A mu d alpha star phi A mu. And then equals using 7.6, so this is the equals as was just mentioned, that it's in that form. Here when he writes, what does equals mean? It means equals as up above here, about the way these things hold up. So that's the case for extensionality. It's in these equivalence classes. It's after a convention, it's after conditions, it's after all these things. And then he has a kind of a longer formula that alpha star of L A mu d alpha A B phi B plus alpha star of L A mu d alpha A mu B phi B plus phi A mu equals alpha star L A mu d sub alpha sub A B d phi sub B, not d alpha sub A B phi sub B, plus alpha star L A mu of alpha A mu B d phi B plus d phi A mu plus dot dot dot. The terms dot dot dot, the ellipsis, indicate terms in dx sub mu. It will not be necessary to be explicit about them. Again, be careful when it says not necessary, sometimes means necessarily not. But here, though, I think it just reflects that when you're looking at otherwise these equations, that you can say that the A star, there's certain particular, if astable configurations, that would make it so that there is a line matching a solution of some kind of way to think then that otherwise something that would otherwise constrain that space will help keep it in one overall orientation and configuration. This is all the configuration space. We can read off from this relation the following rules. Alpha star L, a quantity, sub A mu equals alpha star quantity L sub A mu. So he's brought the term inside, and the term was outside. So by this indexing or whatever, he's reduced the order overall and made it into this inner and outer thing about the products, about the operator rules that apply according to the tensorial products. What make for these operator rules? That the operator calculus is kind of a higher order tensorial analysis, tensorial products. And then he has a alpha star L of that quantity sub B equals alpha star quantity L sub A times alpha sub AB plus alpha A mu B alpha star L of this quantity L A mu. So he's defined in this in the Lagrangian, in both the Lagrangian in its terms and the Lagrangian in its partials, and otherwise these contributions that are the linear and nonlinear parts, and as to whether in terms of the interactions, the least interactions is defined in terms of the difference of this field, grad and grad prime, that these are the kinds of things. He says relation 7.8, which was just read, are what we need. The use of differential forms in 7.7 was not really necessary to derive 7.8, but was presented only as an illustration of their utility. So he might be kind of feeling hinky about that, but otherwise it's something that he probably knows that there's independent things about it. There are non-decidable things about it. There are things that are undecidable about it, whether or not that holds. But here he's just explaining that this is the way to write it so that it maintains kind of a narrative. Their utility. They tell us how the coefficients in the Euler-Lagrange operator change when L is replaced by alpha star L. In fact, we see from 7.8 that if psi in gamma E, then the Euler-Lagrange differential operator associated with the new Lagrangian, i.e. after a minimal interaction sort of change, is this formula minus the other formula, and then suppose that some given conditions or so, then the Euler-Lagrange operator associated with L is is partial minus beta, where beta was defined as beta sub A mu comma B, grad and grad dot, or whatever, equals d beta sub A mu over d phi B sub B. From 7.9, we see that the Euler-Lagrange differential operator associated with this alpha star L is dot dot. One recognizes that it's obtained from this by what the physicists call a minimal electromagnetic interaction, i.e. d sub mu goes to quantity d sub mu minus a sub mu, where a sub mu x are the vector potentials of the electromagnetic field. Thus we may say that in the general case, the functions alpha sub AB of x and alpha sub A mu B of x are the potentials of a more complicated field which has some sort of similarity by generalization to the electromagnetic field. These more general fields are usually called as some sort of generic name Yang-Mills fields. So Yang-Mills fields are fields of potential that have their nonlinear contributions that happen to be able to be written up in grad prime this way, that have for these connections that according to the principle of least action, they still have analytical character that add up make for these potential fields called Yang-Mills fields. So not all fields of potential are Yang-Mills fields, but all Yang-Mills fields are in this sense fields of potential. For a theory of potentials, a theory of some potentials, for example, all the Yang-Mills fields, and a theory of sigma potentials or omega potentials, all the potential fields. We also hope that these calculations illustrate a general point to the reader. As we have emphasized, the use of Lagrangian in quantum field theory is mainly for the purpose of constructing the corresponding Euler-Lagrange differential operators. The more profound aspects of the calculus of variations do not seem to play a key role. Now, Lagrangians is just a function on a bundle sitting over the base manifold. Well, that's nice. He explains that, what is our continuous manifold we started the discussion with? Well, that's the base manifold. It's just a function on a bundle. What is the function on the bundle? Well, that's just the field numbers according to whatever function defines them. And the Lagrangians is just that, is parameterized by T. And as for the bundle and the module. Thus, any sort of geometric transformation on this bundle will induce a new Lagrangian, thus changing the corresponding differential operator. From a purely mathematical point of view, one could just as readily describe things in terms of transformations on the differential operators themselves. Well, that seems nice, and that makes it so that he's helping explain that some of this is organization, and some of this is clarity, and some of this is what makes for tractability with other aspects of the field. That you can have two things that are each sensible and fungible and tractable apart, but the idea is to have stuff that's sensible, fungible, and tractable together. But then also he helps explain that, you can always just lift the whole apparatus about and apply a geometry to it. You could lift the whole apparatus out and apply separation or discomposition. That then when we get into what are these decompositions, the degenerate, the pseudo, the quasi, and how that kind of deconstructivist account gets back to a constructivist account, that we have these notions of that the renormalization was a denormalization, and then it's renormalization, and it's de-renormalization, and then that these effects in the continuum add in, make up for why sometimes it's half and sometimes it's twice. That adds up to keep everything nice, beyond just well-behaved and guaranteed, but accurate. That it's nice to get figured how to make it possible to assign then in these narratives of the extended derivations and all their equivalent forms, what make it possible to then be able to compose those as basically then what can print out to read out a derivation that's formal and make it so all these kinds of nice things about it. Well, that's today's reading. It's from a few pages of vector bundles and mathematical physics. And so it's kind of part of this analysis and methods, or it's about the differential, so it'll be in the vector fields. But hey, have a great day. So long.